Alright, welcome everyone to the fourth video in our complex number series, and we are trying to move away from our irrational numbers, and today's topic is actually quite a neat part, the remainder theorem and the factor theorem for polynomials. So make sure you are following our social media so that you never miss out on future videos. But let's dive right in and have a look how we can deal with these theorems. First of all, the first thing we want to have a look at is polynomial long division. And I know you're probably thinking, oh no, this is exactly what most of my students will be thinking. So let's go through the process and I will show you what we can do to cheat our way through. So first of all, here's our example. We have x squared plus 3x minus 1 is divided by x plus 1. Absolutely horrible. We could be thinking about factorizing here. But unfortunately, the top does not factorize because we have 1 as the number at the end and 3 in the middle, so we're kind of stuck. The only thing we can do here is we can check what do we actually get if we divide them by each other, and we can do long division just like we can do with numbers for equations. Make sure that you know the long division algorithm, otherwise this is going to be a very hard part. Let's walk you through this. First of all, if we're setting up our long division, the part that we're dividing by goes in front of our little squiggly bracket, kind of like a square root, right? Now, what we're going to do is remember in a normal situation, we would check how often does the part in front fit into the first digit. Well, here we can't go digit by digit. We're going to have to go term by term. So we're going to check x plus 1. How often does that fit into x squared? And it kind of feels different and very unnatural in the beginning. So what we actually care about here is we just care about the highest power of x. So we're in the front, we have x plus 1. You can ignore the 1 for now. How often would the x fit in x squared? Well, x times x is x squared, so it would fit x times in. Once we have the number and the top, we're going to have to multiply back. So x times what we have in front. X multiplied by x plus 1, well, if you think about it, we would have to use brackets and expand. So that's exactly what we're going to do. X times x becomes x squared, and x times 1 becomes x. And remember, in the long division algorithm, we're going to have to then subtract everything that we have multiplied back. So x squared minus x squared is going to be 0. That's always a good case because the first part goes away. That's what we want. So now we have 3x minus x giving us a 2x. And remember, we would bring down the next digit, but now we have to bring down the next term, so minus 1. And now again, what do you multiply the front part by to get something with a 2x? Well, we're going to have to multiply by 2 because we need those 2x. We already have an x, we need to multiply by 2, and the number at the end we can fix later. So the next part is going to be plus 2. Now 2 times x plus 1, let's expand that. It's going to be 2x plus 2. And again, we subtract the terms. 2x minus 2x is 0, just like we want. And we're going to get minus 1 minus 2, remember the brackets, will give us minus 3. And now that obviously doesn't fit in x anymore because we have no x. Nothing that we multiply x by is going to give us a negative 3. So we're kind of done here. And remember, in the long division algorithm, if you can't divide anymore, this is going to be your remainder. So what does this mean? This means that this equation here that we've had before is actually the same thing as our part that we've got at the top. Remember, that is the perfect factor. That's how often we can fit the bottom and the top. And then at the end, we have a remainder. So we still have negative 3 to be divided by the number, or in our sense, x plus 1, the term itself. So we've completed one of our long division questions in order to find what the remainder is when we divide. Well, when doing long division, you can find the remainder in polynomial division. Yeah, so this number at the end is what we're interested in, the remainder on what's left. Okay, I'm quite tired after that one. Who needs a breather? If you didn't like this process, as promised, I will give you a much easier way on how to find this remainder. Let's have a look at our first theorem. Now, you don't come a lot of theorems, so say in high school, so what does that mean? Remember, you should know the Pythagoras theorem. There might be a couple of other theorems that you've heard, and theorem in mathematics just means like an idea, a proven fact. Or if you want to think of this as like a abbreviation or a shortcut. So now the remainder theorem is kind of like a rule. So let's have a look what the remainder theorem actually tells us. Here, dividing by x minus a will have a remainder capital R. We also get the remainder R by calculating f of a. So here, the important part is that if we want to find this remainder when we're dividing by x minus a number or x plus a number, then all we actually need to do is we need to switch the sign and substitute it into our previous equation. That seems much easier. Let's have a look at an example, because all of our definitions in mathematics always look harder than they actually are. So our first example is the same one that we've had before, and we're dividing by x plus 1, so the only thing you need to remember is to switch the sign to -1. Now, substitute a -1 into our numerator, the one that we're actually using as a divisor. Now, what do we get? We get p of -1 is equal to -1 squared plus 3 times -1 minus 1. Put that in the calculator or calculate it in your head if you can. Then we get is -3. And we see immediately, wait, that was the answer that we had before, using all of our long division steps. This surely is much easier than what we've had before. So just to make sure that you're really comfortable with this, we're going to do a couple more examples. I blend in the actual rule at the top so you can follow through. Let's have a look at this. We are asked to find the remainder when the polynomial px, x to the power 4 plus 2x cubed minus x squared plus 6x is divided by 2x minus 1. Well, it is a little bit different to what I've written down at the top, but basically what we have here is we can rewrite that bracket here to make it equal to 0. So just like when we are factorizing this, we would solve this for x, so we get x is minus a half. So what we have here is we have our solution for that number that we need to substitute in. And remember, why did we have switched the sign in our rule? Because what we did is we solved for equal to 0. So here we're going to switch the sign, make it negative, and we have to divide by 2 in order to get our value. So all we need to do now is substitute that value in. And just as a reminder, x plus half is one of your factor. That is just the 2x plus 1 rewritten. So we're going to get the polynomial of -1/2. So we're substituting a -1/2 into our equation. Well, now we just get our calculator out, see what we get, and we get -55/16. Well, this is the remainder if our number of our polynomial is divided by 2x plus 1. It's very easy to confuse your positives and negatives, so make sure that you do this nice and slow so you don't get mixed up like I just did. Okay, exam style question. Let's have a look at what a question would be that you would actually get. The remainder of p of x being x cubed plus alpha x squared plus 5x minus 12 when divided by x plus 3 is 0. Find the value of alpha. Well, here we've got the keyword of a remainder. And we can see, well, all we need to find is the remainder. Well, we have been given that this remainder is 0. But since we are talking about the remainder being 0, we still need to think about our theorem and apply this. Let's see what happens if we actually use our remainder theorem here. Remember, we're dividing by x plus 3, so we're going to have to reverse the sign to minus 3. So our remainder is equal to p evaluated at negative 3. And again, we just put this in the calculator. Remember, there's one term with an alpha, so you're going to have to treat it like algebra. Putting our like terms together, we're going to get 0 is equal to 9 alpha minus 54. Well, this is an equation we can easily solve. Plus 54 on both sides, divide both by 9, then we're going to get that alpha is 6, and we're already done. Now, the only thing we really need for exam-style questions here is how to use the remainder theorem using substitution. And remember, you need to switch the sign because we're solving for a root. Now, there is a second theorem, which is called the factor theorem. And it's actually just a special case of our remainder theorem. And you've already used it today. Let's have a look at what the actual rule says. X minus a is a factor of a polynomial px if the remainder is 0 for the polynomial divided by that term. Now, you've actually done this question in the last one. We had a remainder is 0. So the question before is actually an example of our factor theorem. Now, you don't necessarily have to remember this, but the part that we really need to remember is that if we have a factor, then we have a remainder of 0. That is the important part. Because they might not tell you that the remainder is 0, they might just say x plus 3 is a factor. And then from there, you need to know that if it's a factor, that means the remainder is 0. So let's have a look at another example. We have shown that x minus 3 is a factor of this polynomial. Px is x cubed plus 7x squared minus 6x minus 72. Try and give this a go and then check your answers. All right, we're going to start with, we have the remainder equal to 0 and we know x minus 3 is a factor, so plus 3 is the number that we have to substitute in. So the remainder is equal to substituting in 3 into our polynomial. Here's the values that I've substituted in, and we get equal to 0. Well, fantastic. The remainder is actually 0, so yes, x minus 3 is a factor. If this number was anything else but 0, then x minus 3 would not be a factor, because again, we require that the remainder is 0. Awesome. This is all on today's topic about the factor theorem and the remainder theorem. And make sure to check out the first link in the description to all of our courses where you can log in, you can check your process, and you can also check out our premium parts where we have flashcards so you don't forget any of your rules that I've talked about today. And I will see you in the next video. Thank you very much.